If you've ever watched a popular science documentary about gravity, you have almost certainly seen this, the bowling ball on a rubber sheet. It's an incredibly intuitive visual. A massive object creates a dip in the fabric of space, and smaller objects, like planets, naturally roll along that curved surface to create orbits. But as a physical explanation, it's actually pretty flawed. For one, it relies on a mysterious downward gravity pulling on the bowling ball to explain gravity itself. And more importantly, it only shows the bending of space, completely ignoring the warping of time. To truly understand the universe, and especially black holes, we need to move beyond the rubber sheet. We need to look at the actual mathematical blueprint of general relativity. Published in 1915, Einstein's field equations perfectly describe how mass tells spacetime how to curve. But there was a catch. This single line is actually a shorthand for 10 highly complex, nonlinear partial differential equations. They are notoriously difficult to solve. In fact, Einstein himself doubted anyone would find an exact mathematical solution for a real-world object. Enter Carl Schwarzschild. Less than a month after Einstein published his theory, Schwarzschild found the very first exact solution, and he did it while serving in the German army on the Russian front during World War I. Between calculating artillery trajectories under heavy fire, Schwarzschild managed to solve for the exact curvature of space and time around a perfectly spherical mass. This single, elegant equation not only proved Einstein right, but it laid the mathematical foundation for the most extreme objects in the cosmos, black holes. So what exactly is this equation saying?
Before we can read Einstein's mathematical blueprint for a black hole, we need to understand the language it's written in. And that language is all about something called a metric. You are actually already intimately familiar with a metric. Think of a flat 2D grid. If you want to find the incredibly short distance, let's call it ds, between two very close points, you use the Pythagorean theorem. ds squared equals dx squared plus dy squared. If we lived in a purely spatial 3D world, we would just tack on a dz squared. But our universe is a four-dimensional spacetime. To measure the true distance between two events, we have to add time into the mix. But time behaves fundamentally differently than space. In the math, this shows up as a crucial, universe-defining minus sign, minus c squared dt squared. This equation right here is the Minkowski metric, the ultimate rule for perfectly flat, empty spacetime. Conceptually, you can think of any metric as a distance measuring machine. It takes in the coordinate differences between two incredibly close events, your dx's and dt's, and it spits out ds, the invariant spacetime distance. Why is this distinction so important? Because coordinates are arbitrary. They're just an artificial grid we project onto the world. But ds is real. It is the actual physical proper time a stopwatch would measure if you carried it between those two events. The metric is the ultimate translator between our arbitrary human map and the physical territory.
So if flat spacetime is governed by the Minkowski metric, what did Schwarzschild find for a universe containing a single spherical mass? Through rigorous calculation, he discovered that the equation stretches and squishes in a very specific way. Let's break this new equation down, term by term. First, look at the coefficient for time. The rs here is the Schwarzschild radius, a constant proportional to the mass of the object. Since r is your distance from the center, as you get closer to the object, r gets smaller. This makes the fraction rs over r larger, which means the whole parentheses becomes smaller than 1. Physically, this means your proper time, the actual ticking of a clock you carry with you, progresses less for a given amount of coordinate time. This is the mathematical blueprint for gravitational time dilation. The deeper you are in the gravitational field, the slower your clock ticks relative to the rest of the universe. Next, look at the radial space term. It has the exact same factor, but inverted. Because of that -1 exponent, as you approach the mass, this coefficient grows larger than 1. What does that mean for space? It means a small step in your coordinate r corresponds to a much larger step in actual physical distance. Rulers literally stretch out along the radial direction. The mass essentially crams more physical space into the same coordinate gap. And what about the rest of the equation? The angular terms, representing sideways movement around the sphere, are completely untouched. They match flat space exactly. The mass doesn't warp space left to right, it only stretches it inward and outward. What happens if we push this math to its absolute limit? Let's look at the exact distance where the radius r perfectly equals rs, the Schwarzschild radius. If we plug that into our metric, the coefficient for time becomes exactly 1 minus 1, 0. To a distant observer, it looks as though time itself has completely frozen. Meanwhile, the spatial term involves a division by 0, suggesting radial distances stretch to infinity. The mathematics, it seems, just breaks. But to really understand the physical reality here, we need a visual tool: light cones. In flat spacetime, light travels at a constant speed in all directions, forming symmetric cones that represent your possible future. But in this severely warped spacetime, gravity acts like a flowing river, tilting these future cones inward. As you approach the Schwarzschild radius, the cones tip further and further. Exactly at this boundary, the outer edge of your light cone points straight up. This means a photon of light shining directly outward makes zero forward progress. It is just treading water in the flow of space. This boundary is the event horizon of a black hole. Cross that line, and the entire light cone tips inward. Every possible future path points inexorably toward the center. And if you look back at the metric for any radius inside the horizon, something truly mind-bending happens. Because r is now smaller than rs, that parenthetical term becomes negative. This flips the mathematical signs of the equation. The time component becomes positive, and the spatial component becomes negative. Inside a black hole, space and time literally swap roles. Just as you are forced to move relentlessly forward in time right now, inside a black hole, you are forced to move relentlessly forward in space, directly toward the singularity.
So at the event horizon, where the radius equals the Schwarzschild radius, the math seems to blow up. We get a division by 0. But physicists soon realized that this is merely what's called a coordinate singularity. It's a flaw in our chosen map, not the physical territory. Think of longitude lines on a globe. At the North Pole, the coordinate system converges and breaks down completely. But if you actually walk across the North Pole, you don't hit a mathematical wall. The physical ice is perfectly fine. Similarly, if an unlucky astronaut were to fall past the event horizon, they wouldn't hit a physical barrier. They'd pass right through, even though our outside observer's map fails to track them. The true singularity, the breakdown of the physical territory, lies at the very center, where r equals 0. Here, the actual curvature of spacetime becomes infinite. It's the point where general relativity throws up its hands and practically begs for a quantum theory of gravity. But despite this profound mystery at the core, Schwarzschild's exact mathematical blueprint is astonishingly powerful. From a few lines of tensor calculus scrawled in a World War I trench, he predicted the exact geometry of objects that we can now, a century later, actually photograph in the cosmos. But Schwarzschild's elegant solution assumes a perfectly spherical, completely stationary mass. And out there in the real universe, everything spins. To understand the black holes we actually observe, we'll need to step up to the much more complex Kerr metric. But that is a story for another day.